dinner and the beer. Unfortunately, the world isn't that simple, or maybe fortunately for us, because we had an interesting topic for our paper. But I'll still try to make it quite easy.
Good first slide.
Thank you. So some people have been talking about the things on the right, and this is where the types are, or this is where effect systems are controlling what you are allowed to do. There are some people that have been talking about the left, which is where you do things. We in this talk are basically talking about the far extreme left. So that's the context. And we're also kind of similar to effect systems. We're talking about properties of computations. In effect systems, we're adding these annotations to the extreme right, where we're saying what are the effects on the environment, what does the program do to the world, and that's a well-known thing that's been modeled using monads. What we are doing is sort of looking on the other side, and we're tracking what requirements you have on the environment. So what your program or expression needs from the world. And we will be modeling that using comonads. So that's just the sort of formal introduction. Where does the duality come from? And why are we doing this? I said that it's actually not purely dual, so there's something interesting. And that also means there's actually some interesting applications of this Coeffect world. So there's quite a few interesting properties that live on the far left. And in the paper, we are actually looking at two different kinds. One kind is related to variables. So related to the gamma itself, to what variables you're using and how you're using them. Things like variable liveness, where you're tracking whether a variable is used or not. That's one example. I'll have an example that uses bounded linear logic, which is a system that's basically tracking how many times you are accessing a variable when you run your program. So if you say x plus x, you're accessing the variable twice. The other class of coeffects are related to the whole execution environment. So if you look at things like implicit parameters, that's a feature in Haskell which is sort of partly dynamically, partly statically scoped. You can have parameters that are propagated sort of independently of your normal variable bindings. I'll show an example. That's another case of coeffects. There's quite a few practical motivations for this as well. In distributed computing, or if you're doing cross-platform programs, you might want to track what versions of Android your program needs. That's a property of the execution environment. Or if you have GPS sensor and things like that, that's another property that sort of the environment gives you. So I'll start with one variable related example. And this is the bounded linear logic. So what I have here in the orange is a function that takes x and gives me y plus x. Still pretty easy. The tricky thing is x is coming from the bound variable. So that's the function input. Y is coming from the outside, from the declaration side, or the context where I'm defining the function. So if I count how many times is each variable used, then I need to annotate the variable context with something. And here, the angle brackets mean it's a vector. So I'm annotating my vector of variables with a vector of annotations. I only have one variable here with one annotation. I'm using y once. I also have to annotate the function types. So here, because the input of the function is used twice, I'm putting 2 on the function arrow. So coeffects are basically, in this case, tracking how many times I'm using a variable, and we are annotating both the context and the function types with some annotations. Slightly tricky thing, especially compared to effect systems, is that we have a richer structure. So we actually need a vector of annotations for the context. that's one thing that makes the systems tricky and interesting at the same time. So how does this example actually work? Well, in our typing rules for a variable, that's quite easy. When we are accessing a variable, we annotate the context containing just that single variable with 1. So we are accessing the variable once. Abstraction is more interesting because here we actually rely on the fact that the structure of the variable contexts, the gamma and x, is mirrored in the structure of the annotations. So here we know exactly that this part of the vector, uppercase R, I'm using uppercase letters for vectors, matches the gamma, and the single element vector that I'm appending to the end with the s, that's the annotation belonging to the variable x. So when we are doing an abstraction, we know exactly what annotation belongs to the variable, and that's the one we put on the function arrow. Now, because we need to keep this link between the vector and the variable context, we actually can't treat the context just as an ordinary set. So what we are doing is that we have a structural rules explicitly in the system. And this example shows you the contraction rule. So if I have an expression E in a context with variables x and y, and I contract the variables and replace both of them with z, then what's happening in the green bits in the annotations is that we have x and y annotated with r and s respectively. They're single numbers belonging to the variables. In the resulting judgment, we have a singleton vector with r plus s. So if I use x twice and y 5 times, I'll end up with z, which is used 7 times. Contracting and adding the annotations. Now, what we do in the paper is that we look at a couple of different examples of these coeffects or context-dependent computations. So I'll just quickly look at one more example, and this is similar thing, except that here we are actually looking at a different calculus where we can access historical values. So we have a language where we have this pref keyword. You might know it from some data flow languages, but it really just means the function gets the current value of x and the previous value of x plus y. Or if you know some functional reactive programming, this is kind of give me the current value and some value that happened one step before. And here, what we can track is not how many times you are using the variable, but how far in the history do you need to go. So in this case, we need both x and y are under this pref construct. So we need one past value of x and one past value of y. The fact that we are using x before doesn't matter. The first access of x requires just the current value, so that would be annotated with 0, but then we have x under pref, so we actually need one past value of x only because of the second use. And this is the difference in the contraction rule, because this is very similar system, and the key difference is that in the contraction here, we are actually taking the maximum rather than the plus. Because in this system, basically sharing a variable means a different thing. It means we take the historical values and pass them to both of the variables. So that's just an example showing you two different systems that both fit in this very sort of nice uniform scheme. And these two examples are both related to variables, because we were tracking how many past values did we need for every single variable. The other kind of coeffects are related to the environment. So I'm going to show you an example. This is using something like Haskell's implicit parameters. And here I have these question mark name symbols. They are implicit parameters, and just like in Haskell, the idea is that they can come from the declaration side, so they can be lexically scoped, but they can also come from the call side, and they can be dynamically scoped. So it's combining both of the scoping options, and the function here doesn't take anything as an input, and it gives you the current time plus the time zone offset, so you can use it to calculate your jet lag. But there's different ways how we can get these two parameters. So one option here is that the time zone comes from the declaration side. So the environment where I'm creating the function, like Gothenburg, knows its time zone offset, which is +1, but I actually have to give it the current time when I call the function. That's one possible typing, but there's no annotation that sort of forces the typing. So I could also say, when I'm declaring the function, I'll capture the current time and the current time zone, both of the resources, and I'll create a function that doesn't require anything and will access the values from the declaration side. This non-determinism, you could solve it in various ways by requiring some type annotation that would sort of fix one side, and then you could calculate the second one, or do something like that. In Haskell, I haven't quite figured out how exactly that works, but in Haskell it's sort of fixed as well, but you have both of the scoping options. So in our type system, you can sort of express this using typing rule that looks like this. So here again we have annotations. Here, if my body of the function requires some set of implicit parameters that I can split as a union of R and S, then I'll put some of the annotations on the context and the rest of the annotations on the function. So the interesting thing here is that because I'm talking about the environment as a whole, I'm not really mirroring the variable context structure. So here, the annotation R isn't a vector. It's really just a set. And the annotation on the function is also a set. So this is a more different variant where I just have the same type of annotations on both. Important thing to note, it's not the same as the reader monad, because the reader monad will only let you put requirements on the function. This actually lets you sort of capture what's in your current environment and also combine it with the thing that's coming from your function. So let me just ask, how much time have I got, because the timer isn't on? I'll continue talking, and if you feel like I should stop, I'll stop. Because now I have only all the technical details. So if you feel like a nap, that's fine too. But you should definitely read the paper. So I have 5 minutes or something. Okay, yeah. So what's in the paper? There's two interesting things. I only showed you the concrete examples. The paper actually has a nice unified system because it's ICFP paper, which has a sort of defines this abstract Coeffect structure that can be implemented by the set or by the natural numbers tracking the historical values, or by natural numbers tracking the number of uses of a variable. It's interesting semi-ring-like structure. It's slightly more general. We don't have all the required laws for semi-rings, but it's very close to that. The interesting thing is that it has these two operations. One is the one that's used in contraction. That means sort of sharing. The other one is used in application, and it means sequential composition. There's another part which is shape-indexed structure that mirrors the variable context. So you can say either my structure is a vector, or it's a singleton thing, or I could say it's something else, like perhaps a tree. The other thing that's in the paper is that we are looking at comonadic semantics of these things. And this is actually where some of the interesting things happen, because in ffect we have monad over the result, and in our work we have comonad over the input. But there's interesting sort of, the reason why this is not simple is that lambda calculus is actually asymmetric, in that the input structure is a product of variables, so it's a lot more complicated. And to get the structural thing where we have a vector of annotations, you might actually want to say, given a vector, I'll define some data structure where each part of the product has a different thing over it. And it's sort of generalized to work for both of the pair variable or whole variable context cases. So in summary, I think Coeffects are interesting because they actually have some really interesting uses, like liveness, data flow, or various distributed computing things. The other thing is, comonads are cool, or actually in our case, we're using indexed comonads, which is a more general structure that's needed. So I would like to thank my co-authors, Dominic and Alan, because they've done really good work on it as well. And thank you for staying for the last session. I'll do just an announcement, because Dominic has a paper at the Haskell workshop where he's talking about some of the related things to this. You might want to stay for the Haskell workshop.
So, Edward Yang, so in one of the last slides, you mentioned how the lambda calculus is asymmetric. Now, just listening to the previous talk, now I'm wondering, so what happens when you have coeffects in the classical calculus?
That's an interesting question.
It has to do with monads in the classical calculus, because now the asymmetry. Well, no, now you have to do the same thing in both cases. Anyway, just wondering.
Yeah, I think I don't have any good answer, so we can probably continue the discussion later on.
That's an interesting question.
Yeah.
In the typing rules, it looks like, or at least as I've seen in previous versions of your work, there was this kind of choice that we had to make. Do you want a system with either a pair variable information or a global one? And then in the comonadic semantics, you have both that are kind of uniformly integrated. Can you make this uniformity apparent in the syntax, or do we still, when we look at the syntactic part, have to make a choice?
So we've actually sort of the paper has a way of defining the type system so that there's just one type system where you can fit it in both the structural and the flat version. If you want to have a look, it's here. But the key idea is, because we sort of generalize the structure over the context, and then you have the notion of shape, and you can say if my shape is just a singleton thing, then the annotation will actually be just a single value. If my shape is defining a vector, then it will be a vector. And then in the system, you can see these two products, one with the bottom line, one with the top line. They're sort of the key part of the generalization, where in the structural systems where I have pair variable things, they will both be just the same normal product mirroring the structure, but in the whole context world, I can define them as something else. So the one that's used in the abstraction would be the set union. So there's a way to generalize it. I think so if you have to use the structural rules in both of the cases, and the flat system is kind of nicer and simpler in a way because it doesn't need to have all of these extra machinery, but you can define it in a uniform way.
And are there middle grounds? I mean, do you have other things that just a binary, other contexts are just variable per variable? With the generalization, do you have other structures that do not pick these binary extremes?
Yeah. So do we have other things than either per variable or per context? Well, one of the reasons why we've actually written why we are sort of insisting on having a vector as a single annotation for a vector of variables rather than having there's one thing for every variable is that we want to be able to combine them and have properties that have something for every variable and also something for the whole context. So I think that's one interesting system. We've been sort of thinking about having maybe a tree. If you look at bunched logics, they have this interesting tree-like structure. So I'm not quite sure if we can capture that already or if we need something more, but I think that's one interesting direction.
Thank you.
Thanks.
Let's close this session, and so please stay there, and program chair will